ALS 02H. ALS derived indicators for monitoring sustainable forest management. Monitoring sustainable forest management, SFM, is an important step to verify the recovery of the forest ecosystem after a logging intervention. To overcome limitations associated with multispectral images to SFM monitoring, applications based on airborne laser scanning, ALS, technology are becoming more popular in the forest sector. The laser beam is capable to record information from different layers of the canopy, generating a georeference point cloud. This study verified the capability of 4 indicators to differentiate the production unit logging stage. 7 annual production units, PU, located in the western Amazon, Paragominas, Pará, Brazil, were classified into 3 groups based on logging stage: non-logged, 2 years after logging, and 5 years after logging. The indicators evaluated were the number of emergent trees, TOP, average above ground biomass per square meter, AGB, the proportion of clearings per hectare, GAP, and the proportion of low relative density area per hectare, LRD. The indicators were calculated individually for each PU. Higher difference between stages were observed for the GAP and LRD. On the other hand, AGB and TOP were less sensible to the logging stage. In unlogged PUs, the TOP indicator was an average 5.33 individuals per hectare. 2 years after logging, the value decreased by 9%, and 5 years later, the TOP returned to the same level of unlogged sites. The AGB for unlogged areas was 36.2 kilograms per square meter. 2 years after logging, the AGB decreased by 11.41% and by 13% after 5 years, reaching 31 kilograms per square meter. LRD increased 113.3% 2 years after logging, moving from 1.7% to 3.6%. 5 years after logging, LRD returned to a similar level of the unlogged sites, about 2%. GAP increased 2 years after logging by 104%, and 5 years after logging by 200%. Unlogged units showed on average 2.5% of clearings, increased its value 5 years after logging to 7%. GAP and LDR were the most sensitive indicators to monitor recently logging states. Both indicators are clearly associated with logging activities, such as the opening of trails, roads, and tree falling. The indicators were able to differentiate the logging stage, however, they differed regarding sensitivity. ALS 040. Detection of sub-canopy forest structure using airborne LiDAR. Knowledge of forest structure is vital for making sound forest management decisions. Currently, airborne LiDAR data has been well established as a tool to delineate and analyze the structure of forest canopy worldwide. However, what remains less well known is information on the forest subcanopy. Subcanopy structure consists of regenerating saplings, shrubs, herbs, snags, and coarse wood debris. With the increasing density of LiDAR footprints, new opportunities exist to describe these subcanopies structural components in forests that were previously overlooked by other remote sensing technologies. In this research, we used discrete return airborne LiDAR acquired at a density of 22 points per 22 points per meter to estimate sub-canopy forest structure for 50,000 hectares of forest area in northern British Columbia, Canada. In order to do this, we first segmented the forest into canopy and subcanopy based on Lowry's mean height. Lowry's height is a weighted average based on basal area and provides a more stable representation of stand height compared to an unweighted mean height, as it is less affected by large number of small trees. Once Lowry's height was established, we defined the threshold between canopy and subcanopy as 10% less than Lowry's height. Both ground truth forest inventory data and the lighter point cloud were then segmented into canopy and subcanopy components. A mixture of standard height-based and density-based lidar metrics were then computed to develop models to predict subcanopy components of the stands. Models were cross-validated through a forward stepwise regression, with the strongest predictors being P95, leaf area density, and vertical rumple. The vertical rumple, in particular, describes the complexity of the vertical structure of the stand. Using the selected metrics, linear regression models were developed that predicted the basal volume and basal area of subcanopy trees with the R-squared equals to 0.72 and 0.63, respectively. We then applied these models over the entire study area by generating 20 meters wall-to-wall metrics to estimate stand-level subcanopy basal volume and area. These results can be used for forest managers to determine future timber supply and candidate locations for selective logging. Additionally, these attributes can be used to identify fuel loads and potential presence of latter fuels for fire susceptibility assessments. ALS 043, studying tree growth based on a multi-temporal ALS data. Tree height is one of the most important parameters describing a tree. In traditional forest inventories, FI, the heights of the sample tree are measured with a vertex. Due to the increasing availability of airborne laser scanning, ALS data, we estimate the estimation of tree height is no longer limited to a sample plot only, but possible on area-wide level. Based on multi-temporal ALS data, the growth of individual trees can be studied on a wall-to-wall level, which allows new insights into tree growth in relation to the sea level, slope, aspect, crown cover, and tree height. To extract the growth of individual trees, several processing steps are required, such as detection tree positions, finding identical trees, and extracting the tree heights from each ALS data set of different acquisition times. Based on georeferenced ALS point, digital surface models, DSMs, are calculated based on a land cover dependent approach combining the strength of different algorithms. For example, highest laser echo within a raster cell, or moving least square interpolations with a tilted plane as a functional model. As the accuracy of the height difference is strongly related to georeferencing accuracies of the individual ALS data sets, a quality check is done by calculating the DEM of difference, DOD, models of individual DSMs, epochs, for stable and smooth surfaces. For example, open land, street, roofs. Do minimize the height difference to few centimeters, least square matching, LSM, of the DSMs is performed on a tile-based. The derived 3D shifts are applied to the older ALS datasets, whereas the newest ALS data is used as master's DSM and will not be changed. The detection of trees is based on a local maxima search on the DSM and is performed for each ALS dataset separately. In the following processing step, corresponding trees are selected that are present at each ALS dataset. Finally, the tree heights, the growth, and several topographic features, for example, sea level, slope, and aspect, derived from the digital terrain model, and the crown cover derived from the canopy height model, are extracted from each tree. Additionally, the top height is calculated by averaging the heights of the 100 highest trees in a 1 hectare circular surrounding. The described approach was applied for the entire area of the Federal District of Vorarlberg in Austria. For this 2,600 kilometers square region, multi-temporal district-wide ALS data are available from 2005, 2011, and 2017. The derived results were quantitatively validated against the available FI data by comparing the estimated tree growth for the individual FI plots. Based on machine learning techniques, the relation between tree growth, tree height, topographic features, and crown cover were studied. The outcomes demonstrate that multi-temporal ALS datasets are an excellent data source for studying tree growth and consequently for assessing the site index in an operational context.